technical level, so we kind of keep it as simple as possible. Kind of kept it at a low level, but I think you guys will enjoy. All right. So let's get into the exact definition of it. So the fancy definition is that quantum entanglement is a physical phenomenon that occurs when a pair or group of particles is generated, interact, or share spatial proximity in a way such as the quantum state of each particle of the pair or group cannot be described independently of the state of the others, including when the particles are separated by a large distance. So that is the fancy definition. The kind of broken down definition, the real one, is that two particles can be connected such that when you do something to one of the particles, the other particle does the opposite, no matter how far away they are. This quantum phenomenon has been demonstrated with photons, electrons, some quarks, I think. It's a very real thing of the quantum world, and it's freaky because what happens is ever since the 1950s, Einstein and Schrodinger did a lot of research into this. But ever since the 1950s, this has been theorized, and then I believe in the after the 1970s, continuously it has been experimentally shown that you can have these two particles, let's say two photons, and you can get them close together such that they become entangled, which basically means that they're in superposition, kind of like what we talked about last week. And you could take these two particles and you could separate them and take them to the opposite sides of the universe. You could put them light years apart. And the second that you measure, not this, just a second, in the picosecond or however small of time you would like to get, that you measure one of those particles and collapse it to figure out what its state is, the other particle will immediately collapse as well, and it'll be the opposite. So if you're measuring spin of some particle, as soon as you measure it, it is going to be up. One of the particles will be up and the other one will be down. But before the measurement, it's going to be in the superposition. So yeah, does anyone have any questions about this? Or I bet you guys kind of know what entanglement is, or if not, yeah, it's a really cool subject.
Does it have to be the opposite?
Not necessarily, but usually the states work out into equilibrium, and that is shown with a group of particles as well.
But like equilibrium could also be like spin up, right? Instead of
Yeah,
spin up,
yeah,
spin down.
yeah.
So, like,
You're exactly right. You can manipulate these. I guess this is just what's been shown in reality, but you can manipulate these qubits to also do spin up, spin up. But as soon as, based on that manipulation, if you know what you're doing correctly, once you measure one of the particles, you'll know what the other state is given what you did to it previously.
yeah, totally.
Cool. So I got a YouTube video for you guys. I think this will explain it a little bit better. Can you guys hear okay? All right, Teddy, will you just give me a thumbs up? Make sure you can hear the audio of this video when I play it.
Consider throwing a ball straight into the air. Can you predict the motion of the ball after it leaves your hand? Sure, that's easy. The ball will move upward until it gets to some highest point. Then it'll come back down and land in your hand again. Of course, that's what happens, and you know this because you have witnessed events like this countless times. You've been observing the physics of everyday phenomena your entire life. But suppose we explore a question about the physics of atoms. Like, what does the motion of an electron around the nucleus of a hydrogen atom look like? Could we answer that question based on our experience with everyday physics? Definitely not. Why? Because the physics that governs the behavior of systems at such small scales is much different than the physics of the macroscopic objects you see around you all the time. The everyday world you know and love behaves according to the laws of classical mechanics. But systems on the scale of atoms behave according to the laws of quantum mechanics. This quantum world turns out to be a very strange place. An illustration of quantum strangeness is given by a famous thought experiment, Schrodinger's cat. A physicist, who doesn't particularly like cats, puts a cat in a box, along with a bomb that has a 50% chance of blowing up after the lid is closed. Until we reopen the lid, there is no way of knowing whether the bomb exploded or not, and thus, no way of knowing if the cat is alive or dead. In quantum physics, we could say that before our observation, the cat was in a superposition state. It was neither alive nor dead, but rather in a mixture of both possibilities, with a 50% chance for each. The same sort of thing happens to physical systems at quantum scales, like an electron orbiting in a hydrogen atom. The electron isn't really orbiting at all. It's sort of everywhere in space all at once, with more of a probability of being at some places than others. And it's only after we measure its position that we can pinpoint where it is at that moment. A lot like how we didn't know whether the cat was alive or dead until we opened the box. This brings us to the strange and beautiful phenomenon of quantum entanglement. Suppose that instead of one cat in a box, we have two cats in two different boxes. If we repeat the Schrodinger's cat experiment with this pair of cats, the outcome of the experiment can be one of four possibilities. Either both cats will be alive, or both will be dead, or one will be alive and the other dead, or vice versa. The system of both cats is again in a superposition state, with each outcome having a 25% chance rather than 50%. But here's the cool thing. Quantum mechanics tells us it's possible to erase the both cats alive and both cats dead outcomes from the superposition state. In other words, there can be a two-cat system such that the outcome will always be one cat alive and the other cat dead. The technical term for this is that the states of the cats are entangled. But there's something truly mind-blowing about quantum entanglement. If you prepare the system of two cats in boxes in this entangled state, then move the boxes to opposite ends of the universe, the outcome of the experiment will still always be the same. One cat will always come out alive, and the other cat will always end up dead, even though which particular cat lives or dies is completely undetermined before we measure the outcome. How is this possible? How is it that the states of cats on opposite sides of the universe can be entangled in this way? They're too far away to communicate with each other in time. So how do the two bombs always conspire such that one blows up and the other doesn't? You might be thinking, this is just some theoretical mumbo jumbo. This sort of thing can't happen in the real world. But it turns out that quantum entanglement has been confirmed in real-world lab experiments. Two subatomic particles entangled in a superposition state where if one spins one way, then the other must spin the other way, will do just that, even when there's no way for information to pass from one particle to the other, indicating which way to spin to obey the rules of entanglement. It's not surprising then that entanglement is at the core of quantum information science, a growing field studying how to use the laws of the strange quantum world in our macroscopic world, like in quantum cryptography, so spies can send secure messages to each other, or quantum computing for cracking secret codes. Everyday physics may start to look a bit more like the strange quantum world. Quantum teleportation may even progress so far that one day your cat will escape to a safer galaxy where there are no physicists and no boxes.
That was cool.
Yeah. Anyone have any thoughts, questions, concerns about that video? Cool. All right, so let's just get a little deeper into it. So let's talk about the implications of quantum entanglement. So based on the implications, we know that entangled particles can communicate faster than the speed of light, which is really pretty much instantaneously. I think there was a measure of it that I read about, and I think it was something like incredibly fast. It was like 3 trillion meters per second, if not instantaneous. It was like a plus or minus 3 trillion meters per second speed, which just goes to show you how crazy fast this process is. And it's weird that these two particles communicate like that together. It's a really weird phenomenon. a lot of classical physicists don't really like it because it's kind of possibly poke some holes in the universal speed limit theory. But we won't dig into that too deeply. So another implication is that when one state particle collapses, the other will collapse as well. So when they're both entangled and they're in superposition, you know that when you measure one of the particles, the other will also collapse. And if you went to the intermediate lab last week, Teddy talked about BB84, quantum cryptography, and this kind of phenomenon is really useful then, because by measuring one thing, having another thing collapse, you know when your quantum state has collapsed and when someone has attempted to measure it. So it's pretty much when your state is collapsed, that's like a red flag that someone's tried to measure it. So if I'm a secret spy and I want to intercept a message from my commander and I see that the message has been collapsed, that is a red flag for me knowing, oh, maybe the Russians have attempted to read my secret message via quantum cryptography. So that's an application of the phenomenon. Another implication is that the particles, like in a state of superposition, before collapsing, and when collapsed, the particles are polar opposites of each other. So yeah, they're in a superposition of states, and in the video they talked about it. There are actually ways to manipulate it, but you kind of know based on equilibrium that when you measure something, one like spin will be clockwise, one other spin will be counterclockwise. North and south poles, usually polar opposites. You can actually manipulate this, but that's something a little bit more higher level. And this doesn't just have to be two particles. This can be done with a group of particles, which is awesome for quantum computing, because with this phenomenon, you can entangle a bunch of qubits together and perform gates and measurements on them such that all the qubits can kind of cancel out and collapse to your correct answer, which is a really fascinating phenomenon. So yeah, how does this help with computer and information science? We have another video where this guy kind of goes over um, entanglement from a qubit perspective.
This guy's awesome.
You guys enjoy.
This guy's awesome. This guy.
Really understand.
Oh, I'm sorry. Sorry, I think my audio is messing up for some reason. Try that again.
We can hear it.
Really understand.
Wow. Are you guys hearing that audio kind of? Yeah, let me try to fix this real quick. Very sorry about that, guys.
You're good. No worries.
Good, no worries.
Hey, Teddy, do you want to do me a favor?
What's up?
I think this is an issue with my computer because do you think I could stop the share and then I shared the presentation with you? Do you think you could go to it and then play the video?
Open that. Yes, sir. Open that.
Thank you very much. Sorry about that.
No worries.
No worries.
Apologies about that, guys.
Oh, you're good, man. There it is. Okay. Can you guys see that? Like the entirety of the screen?
It's a little wide, but it's good. It's good with me.
Here, let me I can just present it like over here. this. Ugh, it's just gonna respond like that. Yes. Can you hear it?
I cannot, unfortunately.
Hmm. Hmm.
Still can't hear it, unfortunately. Have you unplugged your headphones? That should work. Yeah, now we can hear it.
The superposition of the 0 and 1 state of a single spin is simply.
Well, now I can't hear you.
I can hear it just fine.
To really understand.
Okay, type in the chat something if you can't hear it. Otherwise, I'm gonna play it like this. Chat. Can you not hear me then?
I can hear you fine, just steady.
To really understand what is special about quantum bits and why they can provide such a large computational power, we need to look at what happens when we take more than one qubit. Let's take example of a spin, which we know how to visualize. The superposition of the 0 and 1 state of a single spin is simply the spin pointing to the right. So that doesn't seem so strange. But now let's take two spins and make them interact with each other. This can happen, for example, because each spin produces a tiny magnetic field in its vicinity, and this field changes the energy of the other spin. Remember that we can rotate a spin by applying an oscillating magnetic field at the frequency proportional to the energy difference between the 1 and the 0 state. But if there is another spin in the vicinity, the total energy depends also on the state of that spin. Let's say I prepare both spins in the 0 state, and then I put spin A in the superposition of 0 and 1. Now I try to flip spin B by applying the frequency it would respond to if spin A is in the 0 state. But actually, since A is in both the 0 and the 1 state, then spin B both flips and doesn't flip. The resulting state is a superposition of 0, 1 and 1, 0. The 0, 1 branch of the superposition is created because spin B flips to 1 when spin A is 0. And the 1, 0 branch is created because spin B remains 0 when A is in the state 1. This kind of superposition is perfectly legitimate, but it's really special. In this state, I have absolutely no idea of where the two spins are pointing, but I do know that they point in opposite directions. This is called an entangled state. If I separate the two spins after I have prepared the entangled state, and I measure, for example, spin A, and I find it in the 0 state, then instantly spin B acquires the 1 state, no matter how far apart it is when the measurement takes place. This is what Einstein called dismissively the spooky action at a distance. But now we know from many experimental tests that this is the way quantum mechanics really works. In the context of quantum computing, entangled states represent a strikingly non-classical computer code. There is no way you can write in your desktop computer a code where 2 bits have no value but have the opposite value. But you can do so in a quantum computer. And the more qubits you have, the more these entangled quantum computer codes proliferate and grow exponentially with the number of qubits. Gaining access to these entangled quantum states is the key to exploiting the exponentially large computational power of quantum systems. At the same time, entangled states are very fragile and can easily be destroyed by unwanted interference from the outside world. This is why building a quantum computer requires so much effort and investment. We need to create a perfectly controlled environment where large entangled states can be produced and manipulated without interference.
Let's see. Do you want to switch over to your screen, Will, or is that I can just leave this here and you can talk about that if you'd like.
Can you hear me, Teddy?
Dang it, I cannot hear you. Weird. Test. That's
Hey, what's up?
weird.
Can you hear me?
So I am on audio headphones. I don't know. I guess just ignore me. I'm gonna be lost for the rest. I wonder if you can hear me. Oh, okay, cool. Just share your screen if you want, Will. And you can just like pretend like I can hear.
Yeah. So anyway, sorry, Teddy. But I just had one last slide, so you got to the most of it. It was just pretty much that a quantum computer can take advantage of this entangled property by taking qubits and intertwining them so that one measurement can collapse the entire state. And you can kind of, through a singular action, you can affect the entire state of qubits. And this kind of effect of value sharing through the entire system is really important in Shor's algorithm, which is the, if you've heard the like people say quantum computing can break all of encryption and break Bitcoin and all that stuff, that's Shor's algorithm. Phase estimation, which is something pretty cool that we can get into kind of later, and quantum counting, also something pretty cool we can get into later. But it's super important to understanding quantum speed up, because that is like the whole beauty of quantum computing, is that with normal classical bits, you have singular bits that don't really interact with each other. They're just a means to store values, and we've gotten really good at doing them really fast. But via quanta and entanglement, we can have an entire system of qubits that act as a collective. And when you affect, just with one slight effect, it can change the entire entity of the entire system. And this is really important because this is how the real world works. Because for Shor's algorithm, for instance, the reason it's able to break encryption is due to prime number factorization. Prime numbers have these really weird, funky patterns that classical computers can't pick up on. But because of this ability to have all these qubits in a singular value sharing state, it can detect those patterns and collapse to a singular answer much faster and better than a classical computer can, in a really cool way. So that was all I had for the day. Does anyone have any questions?
I do. So you say that if you collapse the state of one qubit, the one that's entangled with it will also collapse, right? But when we observe an element that's in a quantum state, we collapse it anyway. So how do you know?
Well, so observation is measurement.
Yes. As soon as we observe it, right? So let's say we have bit A and bit B, right? You observe bit A and you collapse it into a state. You're saying that bit B is collapsed into a state, but how would you know? Because if you observed it, it would collapse anyway, not because you observed bit A. Do you see what I'm getting at?
Oh, yeah. I see what you're getting at. I guess it's just because by observing through this process of entanglement, I think the beauty of it is that it's already collapsed by, so for instance, collapsing bit A, if we know that it can either be 0 1 or 1 0, so if we know that they're polar opposites, if we collapse qubit A and we have a value of 1, we know the value of qubit B because it's 0. Does that kind of make sense?
Well, I know that we know that it's going to be, but it's just that you say that it has already collapsed into that state. I'm guessing. I guess I don't understand how you would know that it collapsed at that point and not just coincidentally when you observed it the second time.
So there's like certain gates that we could use. The Fredkin gate is one, and like what that does is it's like a transfer of like information, or like information of the state of a given qubit or system. So like you can imagine that like we have like very like say we have like these like set of qubits, or like 2 qubits to keep it simple, right? And we entangle them and we measure one, and then the issue is, well, like of course we would look at the other one and it would be collapsed, because that's looking at them and that's when they collapse. But like we don't actually have to look at that specific qubit. What we can instead do is we can not copy but transfer the information of that qubit, which is the probability amplitudes, like, or the possible states and the probabilities of each state that it can be in, into an ancillary, I believe is how it's pronounced. A qubit, just a qubit that we use kind of like as like extra space to do operations. So we can put it into this like extra qubit, and then if this extra qubit interacts with another qubit by like performing like we can perform a conditional operation on this gate, and we can say if this gate is in a superposition of x and y, which is what we programmed it as before this entanglement and this collapse of the other states, then do such and such operation. Based on this kind of like conditional logic flow, we can actually set up for not measuring it completely, but instead transferring the information of that state to another state, which isn't necessarily cloning, because you don't get 2 states in the end. You still get 1 state, and then doing conditional operations based on like whether that qubit is entangled. And of course, like it wouldn't be entangled if the other state had already collapsed and caused it to collapse.
Okay.
Yeah, I think it is funky how you don't need to measure, like, but whenever you measure the state, it's kind of that's a whole process, and that's something. So you can kind of use quantum information without measuring it to then perform other observations so that you can then get to a measurable state. If that makes any sense.
I'll run with it for a while.
Apologies. I will look into a better way to answer that question. I think I just need to do a little bit more reading, and yeah. Does anyone else have a good way of answering that question? All right, well, that about sums up the presentation. Does anyone have any questions, comments, concerns? Anything about entanglement? Any cool phenomenon or anything they'd like to mention?
Not for me. So we're going to be having this at the intermediate lab at 6 o'clock. I'm thinking since it's like 30 minutes away, I'll just close the Zoom and then open it back up like 5 minutes before. Excuse my dog going crazy. What we're going to be doing today is setting up a quantum computing development environment. And so like very basic stuff like downloading Python, getting Miniconda on your machine, and then getting Qiskit, the quantum computing module that we're going to use. So yeah, thanks so much for coming all, and we'll see you at 6 if you so choose.
Yeah, thank you so much, guys. All right, cool.